Okay, let me go ahead and share my screen and we'll go on to the next slide. All right. Here we go. Here's some detail on the various orbits that we covered, the three orbits from 1991, 97, and 2010. We will have a paper coming out so you can look at the details on this slide a little when that paper is ready. Our observational data, the visual magnitudes that we were able to collect from the International Comet Quarterly totaled over 2,000 by observers from around the world. And here are three of the three apparitions that we covered, some information about the pre-perihelion, post-perihelion observational data. And so our problem then is to correlate the water production rates and the visual magnitudes to give estimates for important properties of the comet. The SEMVM model, which is just very briefly summarized. Again, I would remind you that we do have two posters in this session too, where you can look at more details on the model, and we do have references where you can look at that too. However, that's very useful for determining the water production rates, mass gas release rates, mean effective surface areas, and minimum nucleus sizes. We also assumed a fairly typical cometary abundance for Hartley 2 taken from a multitude of mini space and ground-based observations. The anomaly for Hartley 2 was mainly that it had a very high CO2 mixing ratio, 20% relative to water, and very low CO. Usually those two are reversed in typical comets, as you can see in table 3. The results, well, we were able to use the model to produce water and gas production rates, both pre and post perihelion. We gave power law fits to and other properties that are now summarized in table 5. I know there's a lot of information there. I'll summarize that at the end of the talk. Here are some of our figures that we were able to generate. Figure 1 over here on the left gives the water production rates as they are related to the visual magnitudes for the three apparitions. So you can see there's a fairly tight correlation there, and the fact that the 1991 return had higher water production rates in general near perihelion, followed by the 97 apparition having lower, and the 2010 had the lowest production rates. On the right-hand side, we give the variation of the visual magnitudes with heliocentric distance, both pre-perihelion to the left side of the graph and post-perihelion on the right side of the graph. This is for the 1997 apparition only. Figure 4, some more results, variation of the apparent visual magnitude with heliocentric distance around perihelion. So you can see the peak of perihelion and the very steep increase pre-perihelion, followed by a more gradual decrease post-perihelion. In figure 4 on the right-hand side, we give the temporal behavior of the water production rates with the time measured in days before and after perihelion. You can see that there is some scatter in the data. Of course, some of the scatter comes from inaccuracies in the estimates of the visual magnitudes. However, we think that there are very identifiable peaks that we see. Peaks meaning that there are diurnal variations where the water production rate does peak up on a very short time scale. And there are also outbursts. So we're looking at these two types of phenomenon to explain some of the peaks that we see in these figures. And here's a result where we give the variation of the active surface area with time from perihelion for the 3 apparitions. So you can see the active area of the surface of the comet measured in square kilometers. Median line may be around 1 kilometer. Around perihelion, of course, it peaks up. Further from perihelion, it's lower. And post-perihelion, in general, it stays higher. So our SEMVM model results, we're able to show the correlation between the visual magnitudes and the water production rates. When we look at the volatiles that are lost, we can measure that in terms of kilograms per second for all 3 apparitions. And here we give the numbers that we get. You can see that its greatest volatiles lost are greatest for the 1991 apparition, from 4,200 to 5,620 kilograms per second, all the way down to the 2010 apparitions, which was as low as 340 to 405 kilograms per second. In general, the water production rates are higher post-perihelion than pre-perihelion, as we saw in some of the graphs that were presented just in the previous slides. We also were able to calculate active surface areas in square kilometers, and I summarized these as you saw in one of the figures before. We find that on average about 7 to 0.4 square kilometers were found to be active surface areas, consistent with minimum nuclear sizes of about 0.75 kilometers, 0.4 kilometers, 0.14 kilometers, respectively for each apparition. So the first numbers, of course, pertaining to 1991, second number, 1997, 2010 for the last number. You can see again, there's a decrease as we go from apparition to apparition. We do find that there is hyperactivity indicated, meaning that we believe that the active surface areas in some cases exceeded the nucleus surface area, which would indicate that there are distributed sources of water carried by more likely icy grains that are leaving the comet. Icy grains containing water that then heat up in the coma, and the water is then released from the grain rather than just the nucleus surface. Water production rates, as I mentioned, they decrease about 4.5 times from 1997 relative to 91, and about 3.5 times from 97 to 2010. These are due to some slight orbital changes. So possible changes in perihelion distance, possible seasonal changes. So aspects of various parts of the comet are being illuminated during the orbit. And even we believe there may be signs for aging of the comet during this short time period. So we can see that the model results also indicate that Hartley 2 lost about 16% of its lost mass per orbit in 1991, about 5.6%, in 97, 1.6%, 2010. That would be the total volatile mass loss compared to the total nucleus mass per orbit. And our general conclusion then would be that the SEMVM method is an efficient and alternative method to finding loss rates for water and total gas production properties. It is in good agreement when we look at spacecraft or ground-based observations during these time periods. And we think a very powerful part of this method, or aspect of the method, is that the visual magnitudes fill in a lot of additional dates that are not available from ground-based or space-based observations. So we can really look at what happens in between some of the ground-based and space-based observations. We can fill in that part of the behavior of the comet. So if we're looking, for instance, for outbursts or diurnal variations, we have a cadence of measurements, which is much more frequent with the approach that we're using than we could ever have from using major telescopes from the ground or space-based observations. Here are some acknowledgements and a reference list. And that's going to bring me to a close of my talk. I appreciate your attention during the talk. And if there's any remaining time, I would be more than happy to entertain questions about this. Again, let me remind you, we do have 2 posters at COSPAR on the Comet Kohler and Comet Virtanen using the same method. And you can find more details about the method in those 2 posters. There'll be short audio presentation given about those a little bit later. Okay, thank you very much. Bye.